Hi, my name is Anika Valaru, and this is my lab report for Lab 3 in Physics 2212. The purpose of this lab is to use the principles of energy conservation and current conservation to model and observe various circuits. The models and principles involved are Ohm's law, capacitance, node rule, loop rule, and this other equation as mentioned in the lab instructions. Assumptions and initial conditions include there are no outside forces acting on the models, and components do not have resistance unless stated. Materials involved were the online circuit construction kit and a spreadsheet app like Excel. So for a preview, for a round trip around the circuits, the sum of the individual potential differences should add up to 0, as you can see through this graph. For part 3, as the resistance in a bulb increases, the time it takes for the capacitor to charge and discharge increases. It also takes longer for a capacitor to discharge than charge. And in part 3.1, the experimental data and the graph data match, which we'll see later. The main ideas, so we're looking at circuits, resistance, capacitance, energy conservation, and current conservation. The system will be the model shown, and the surroundings will be everything else. So charge conservation and energy conservation in series circuits. So for this, the first circuits, the circuit components are two 1.5 volt batteries, one 47 ohm resistor, one 100 ohm resistor, and two ammeters. So you can see the circuits on the right. The prediction would be the I equals V over R, which ended up being 0.024204 amps. Then the simulation, you can see that it's 0.02 amps, and in the reversed ammeter it's also 0.02 amps, so everything matches. For this next one, the circuit is open, and there's a voltmeter involved, and one of the ammeters was taken out. So ammeter at I1, which is the one up here, was removed. The voltmeter reading is -3 volts. The ammeter 2 reading is 0 amps. And the explanation is since the voltmeter has infinite resistance and is part of the circuit, the ammeter reads 0. The 3 volts is the total volts from the battery. And the circuit components for this one are the same as before, except now it's closed. I is still 0.02 amps. For a round trip around the circuit, the sum of the individual potential differences should add up to 0 as mentioned before. So delta V equals 0. Because the resistance is high in the voltmeter, the current it draws is negligible, so the reading on the ammeter does not change in this instance because the voltmeter is not part of the circuit. So here you can see the volt differences as mentioned in the different parts, and here you can see the graph of all that. So now we have two ammeters, one in parallel, not just in series. So before the parallel ammeter, it was 0.02, now it's 0.06, and because the ammeter is in parallel, the resistance decreases and the current's reading is higher. And here you can see the different resistance measurements for different parts of the circuit. For the RC circuit, now we have a 9-volt battery, a 10 ohm bulb, and 200 mF capacitor. With the battery, the light is bright at first but then dies down. Without the battery, the same thing happens but slower. So in both scenarios, there's a large current at first but then it diminishes. The time to charge is 5.58 seconds and the time to discharge is 7.03 seconds. So now we have a 20 ohm bulb instead. The same thing happens except it takes longer than it did for the 10 ohm bulb. The time to charge was 9.34 seconds and the time to discharge was 14.18 seconds. So time-dependent voltage across a discharging capacitor, RC circuits. So now we have a 9-volt battery, a 30 ohm bulb, a 200 mF capacitor, 1 voltmeter, and a timer here. And so I connected the voltmeter across the capacitor and used the timer to measure the voltage at different times across the capacitor. And this is the delta voltage versus time graph. And then, so now we did, to make it a straight line, I used this equation here, and so now this is ln delta V over delta V naught versus time graph, which makes it a straight line, and you can see the slope is negative 0.1657, and for RC, since RC is negative 1 over the slope, you get 6.035, and from the experiment data, we found that it's 6, so they match. Similarities, the RC values were about the same. There were no significant differences. Errors, time increment readings, or voltage readings at those time increments may not have been exact. What if we were doing the same experiment but used an actual ammeter? An actual ammeter has more resistance than one in the model, so the readings would not have been as accurate. And then what if you were doing this experiment in real life, but with a real battery to charge a real capacitor with no resistor in the circuit? The capacitor would be expected to charge instantly, but that is not what would happen because in reality each component has some resistance, so it would take some time.